Hi, my name is Sigurd and I'm a consultant at the Danish Technological Institute. In this course we're going to look into Vat Photopolymerization, also known as VPP. Taking a look at the main technology chart with AM technologies, VPP has its own category with 3 undercategories. The first is stereolithography, also known as SLA. Then we have digital light processing, DLP, and CDLP, continuous digital light processing. If we look at the ISO standard, we can see that the material is polymer. The fusion state is chemical reaction bonding, which means that a chemical reaction glues the part together. The material feedstock is a liquid, also known as resin. The material distribution happens in a vat, which is a container with resin. And the basic AM principle is light reactive photopolymer curing. The process category is Vat Photopolymerization, also known as VPP. First up, let's have a look at what Vat Photopolymerization is. As mentioned earlier, there's 3 types of VPP: SLA, DLP and CDLP. The main difference is the light source. SLA cures with a laser, DLP cures with a projector, and CDLP cures with LED and oxygen. VPP printers work in 2 different ways that has to do with elevation. We have bottom-up and top-down. With bottom-up, the light source hits from below. You print on the downside of the platform and the platform is lifted up. This technology has low cost and is widely available. For top-down, the light source hits from above. You print on the top of the platform and the platform is lowered during the build. The benefit of top-down is that you have a very large build area and faster build times. There are different downsides to the 2 elevation technologies, which you can see below here. A VPP printer consists of 5 main components. First, we have a vat of liquid photopolymer, which is the container consisting of uncured resin. And then we have the light source, which is different from SLA and DLP. SLA uses a laser and a mirror to point the laser at where to print the part, and DLP uses a projector to print each layer as an image. There's also a recoder that ensures you have an even layer of resin to print in. Then we have the build platform, which the parts are built onto. And finally, the elevator, which lowers or raises the build platform. Looking into the process flow of VPP, first you're going to insert resin and build platform. Then you distribute resin in an even layer. After that you solidify the layer with the light source and move the platform up or down. If you use bottom-up technology, you add resin, but that is not necessary for top-down. This process continues until you have the full part. Finally, you have to clean the prints for excess resin, remove support and cure with UV light. VPP printers come in different sizes and prices, from small desktop printers to large industrial printers. To the left you see an example of a desktop printer and to the right you have an industrial printer. The main difference is the size of the build chamber, the print speed and of course the price. Desktop printers mainly use bottom-up technology, where industrial printers use top-down. A VPP printer consists of 4 main components. First, we have a vat of liquid photopolymer, which is the container consisting of uncured resin. And then we have the light source, which is different from SLA and DLP. SLA uses a laser and a mirror to point the laser at where to print the part, and DLP uses a projector to print each layer as an image. Then we have the build platform, which the parts are built onto. And finally, the elevator, which lowers or raises the build platform. Looking into the process flow of VPP, first you're going to insert resin and build platform. Then you distribute resin in an even layer. After that you solidify the layer with the light source and move the platform up or down. And then you add resin again and continue the process until you have the full part. Finally, you have to clean the prints for excess resin, remove support and cure with UV light. Looking into elevation, there's 2 types of technologies, bottom-up and top-down. With bottom-up, you print on the downside of the platform, lifting the platform up through the print. This technology has low cost and is widely available. With top-down, you print on the upside of the build platform and moving it down through the print. The benefit of top-down is that you have a very large build area and faster build times. There are different downsides to the two elevation technologies, which you can see below here. VPP printers come in different sizes and prices, from small desktop printers to large industrial printers. To the left you see an example of a desktop printer, and to the right you have an industrial printer. The main difference is the size of the build chamber, the print speed, and of course the price. Desktop printers mainly use bottom-up technology, where industrial printers use top-down. In this video we see a desktop SLA printer using the bottom-up technology. Here you see an example of a top-down printer. The recoater distributes the resin, and then the laser solidifies the part. In the end, we see the part emerging from the resin. Now it's time to look at the pros and cons of the VPP technology. When talking about 3D printing, you often talk about visual appearance and functionality. With VPP, you get both. On the visual side, you can get transparent materials and a very nice smooth surface. On the functional side, you can get high tolerances, you can get flexible parts and heat-resistant or biocompatible parts. One of the main benefits with VPP is high surface finish and accuracy. You get a surface finish down to 10 microns for industrial systems and a dimensional tolerance of plus/minus 0.5%. The main downside of VPP is material properties and longevity. The materials are often brittle and the parts can break easily. Also, you have a problem with loss of mechanical properties over time due to degradation in sunlight. Another downside is that you have to account for resin curing and runout. For instance, internal structures are difficult to cure and you need runout holes to allow for resin to drain. The reason why you need to drain uncured resin is that the boundary between uncured and cured resin can create tension during UV curing. This can cause the parts to crack. Another benefit with VPP is that you get a lot of different materials with different properties for different purposes. VPP is fast for prototypes and slow for large volume production. The printers are good for injection mold prototypes, investment casting and general prototypes where you need a high finish and quick print times. SLA and DLP is rarely used for production of industry parts except in certain areas such as dental and hearing aids. But some CDLP machines like the Carbon 3D printer are suited for medium to high volume part production. The total printing process time depends on the printer and the amount of parts you print. Below you can see an example of what the total printing process could look like with setup, printing time, wash and cure, and support removal. Let's sum up on the pros and cons for VPP. The benefits include high surface finish, fine details, high accuracy, you can get many different materials, it's good for prototypes, and you can get printers in many different sizes. On the downside, the parts are brittle, you need support, the parts are UV sensitive, you need extensive post-processing, you have to account for resin runout and curability, and the process is more complex than FDM. Now we'll look at the different design possibilities. With VPP, you can make very small features with high resolution, as you can see on the pictures below. The minimum feature diameter for a standard printer is no more than 0.2 millimeters, but of course it depends on the printer. Another design possibility with VPP is lost wax casting. Here you can make very complex casting models. The way you do this is by 3D printing a wax model. Then you make a mold around the printed model, and then you pour your casting material into the mold. Then the wax disappears and you can remove your complex part from the mold. With VPP you can get high temperature resistance. It's actually possible to print resin parts that can withstand temperatures over 300 degrees. It's also possible to print elastomers, which are flexible rubber-like materials. These are often used for printing shoe soles, as we see here. To sum up the design possibilities, you can print small feature sizes with high resolution, you can cast complex parts and print flexible materials. Now we'll have a look at the different design guidelines. In this overview from HOPS, we can see the different design rules for VPP. I'll focus on support and overhangs, embossed and engraved details, escape holes, and tolerances. The general rule is that you need support whenever you have an overhang. This is because the weight of some features can deform your design during the printing process. You can avoid support by making the part self-supporting, as you see on the picture to the right. In the top right corner you see an example of support for the top-down technology. Below you see an example of the support for the bottom-up technology. It's possible to have embossed and engraved details with VPP printing. To make sure these details are visible, they need to have a minimum height or depth of 0.4 millimeters. For VPP technology, it's important to have escape holes and channels to drain out resin. The minimum recommended size for holes and channels is 4 millimeters. The best way to design channels is with rounded corners to make it easier for the resin to get out. Escape holes are especially important when printing cup-like structures with the bottom-up technology. If you don't have escape holes, you risk print failure or blowouts, as you see in the picture below. The standard tolerances for VPP are plus minus 0.5%, but it depends on the size of the part. You should try to avoid large flat surfaces, thin walls, abrupt changes in cross-section area, and holes printed in the XY direction. And you should pay attention to how you orient the part. These are just guidelines, but the reason we have them is to make sure that what we design is also what we get out of the printer. Now it's time to look at the different materials we can print in. As mentioned earlier, we have a lot of different materials to choose from. For example, you can get tough, rigid, durable or flexible materials. The materials are designed for different uses and you can get different colors and properties. So make sure to choose the right material for your specific purpose. You should be aware that all materials are thermosets, so they cannot be recycled. If we compare material properties for resins to SLS printed PA, we see, for example, that elongation and impact strength are typically lower. It is possible to find resins where these properties are higher, but then other properties will be lower. So it's important to choose the resin with the properties that fit your part. Here we look at stiffness for Formlabs desktop printers, which are among the most popular on the market. What we can see is that Formlabs SLA materials covers almost the entire range of traditional plastics. When printing with flexible materials, you get rubber-like properties with high elongation at break and with high softness on the Shaw A scale. Now it's time to look at what we can print with VPP. One area where we see this printing technology used is shoe soles. This is because you can print in flexible materials and it's even possible to make custom fits. VPP is also very popular for dental and medical use. For instance, 97% of all hearing aids are produced with this technology. One of the reasons is that you can get biocompatible materials that are classified as 1 or 2A. VPP is one of only 2 technologies where you can print in transparent materials. So if you want to print something transparent like the lampshade you see here, this is the technology to use. Finally, VPP is great for testing molds for injection molding and making complex casting models. Let's start with health, safety and environment. Before printing with VPP, you should always read the safety datasheet. Furthermore, you have to use the proper safety equipment. This includes ventilation, masks, glasses, gloves and proper work clothes. When printing with resins, there are some safety measures you need to take. First, the operator needs an epoxy certificate course. You should also be aware that uncured photopolymer resin is classified as hazardous to aquatic life. Also, the laser beam is harmful to the eyes, so avoid direct contact. Isopropyl alcohol is a flammable chemical. Make sure to clean and cure parts according to the material specification. VPP printed resins are not approved for use with food, drink or medical applications on the human body, but VPP printed parts may be approved for use with medical applications. We looked at the printing process itself in a previous chapter, Now we'll look at the steps that come before and after. First, you need to find the parts you want to print and open them in the preparation program. In this bottom-up example, we have 5 different parts and 16 parts in total. Next up, we need to orient the parts according to the printer type. Since this is a bottom-up printer, we have angled the parts slightly. If it was a top-down printer, we would have placed the parts flat on the platform. Next up is nesting, where we place the parts correctly on the platform. Here we want to place as many parts on the platform as possible, and since we can only print in one layer, we want to avoid overlapping parts. Now we need to make the support structure. The support material is the same as the build material, but there is a difference between printing with bottom-up and top-down. Top-down printers has very few design restrictions and parts can be oriented in any direction. Flat alignment is often the best as it uses least amount of support and gives the fastest build time. For bottom-up printers, support structure is a bit more complex. Here you want to reduce the cross-section area to minimize the risk of failure in the build job. Therefore you need more support and this increases the build time. Next up is scaling, which is necessary because parts contract during cooling. How much a part contracts depends on the material and is mostly an issue for large thin surfaces. Scaling is typically handled automatically by the preparation software. Now we need to prepare the printer. This includes adding or changing resin, preparing the platform and uploading the job. When the printing is done, we need to unpack the parts. The way you remove parts from the platform is with a spatula like the one you see here. With the bottom-up printer, you need to remove the platform from the printer and turn it around. With top-down, you can remove the parts directly in the printer, but you can also remove the platform before you do it. After unpacking, it's time to clean the parts. Here you can use isopropyl alcohol or an ether known as TPM. To help cleaning, you can use different brushes, such as a toothbrush or paintbrush. It's also possible to get a machine that can handle part of the cleaning process. Now it's time to remove support. Here you use different tools, such as pliers or knives, but be careful not to break the fragile green part. The reason why the part is green is because it hasn't been UV cured yet, and that's the last step in the printing process. Here you expose the parts to light and heat, and it's essential to finish polymerization. The settings for this curing process depends on the material. After printing, we have to post-process our parts, and we're going to look at that now. You can post-process VPP parts in different ways. The most common ones are sanding, mineral oil finish, and painting. I'll cover these in the next couple of slides. First, we have sanding. There are 2 types of sanding, wet sanding and dry sanding. The recommended grit size for wet sanding is 800 to 1000, and for dry sanding it's around 600. Sanding is typically used to remove support marks on the parts. After removing support marks, you can polish with mineral oil to hide the white spots from sanding. You also get a great visual surface finish from mineral oil, and it helps with friction. Finally, we have coloring. Colors are often added in the resin, but you can also paint the parts afterwards with spray paint. Painting is also a great protection against overcuring by UV light. That brings us to the end of this course. Thank you for watching. Here we have a few links for further reading. First, we have some general links about additive manufacturing. And here we have some specific links about VPP. That brings us to the end of this course. Thank you for watching.